Our speaker for today is Professor Sayam Sen Gupta. Professor Sen Gupta did his undergraduate degree in chemistry from the University of Calcutta, followed by his master's at IIT Kanpur. He then moved to United States where he finished his doctoral degree from Carnegie Mellon University at Pittsburgh. After two postdoctoral stints in US and Germany as a Alexander von Humboldt Fellow, he joined NCL as a scientist in December 2006, where he was a senior scientist in the chemical engineering division. He moved to IISER Kolkata in 2016 as an associate professor and is currently professor in the Department of Chemical Sciences. He is an inorganic chemist by training and works in the broad area of sustainability, particularly in bio-inspired catalysis and materials. He also teaches sustainability and chemistry at IISER Kolkata, a course which he co-developed. Thank you, Professor Sen Gupta, for joining us. The stage is all yours now.
Thank you, Neha. Thank you so much for the very kind introduction. And first of all, let me thank ACS for giving me this opportunity to reach across to several people and talk about a part of the work which we do in the lab. So thank you very much again, once again, Neha, Manas, Aparna, and others in ACS. So again, I'll talk about my lab works on various different things, but we have one area which we have been working for quite some time. That is this bio-inspired iron complexes for sustainable oxidation reaction. And we're going to talk about, I'm going to talk about a very, very, very simple reaction, which is converting a CH to COH, hydroxylation reaction, probably the most elementary reaction you can imagine. And the reason we are very interested in installing OH groups in hydrocarbon fragments, because I've shown you a few natural products here, like erythromycin, morphine, Taxol, and probably all of you know this name because they're all drugs, and these are all natural products. And there are several natural products like this, and all these natural products, one of the things we would see is that they're very specific OH groups on their hydrocarbon backbone. Now, one of the endeavors of medicinal chemistry has been to sort of try to make all these compounds, so that allows you to make different varieties of this, maybe install more OH groups, more other functionalities. And that has been a big thing in organic chemistry. And most organic chemistry reactions essentially still very much, rely upon our electrophilic nucleophilic substitution reactions. That's the way we have learned to build fractals. But nature makes things in a very different manner. For example, for the Taxol biosynthesis, which I've shown here, you could see that the nature first makes this hydrocarbon framework and then uses cytochrome P450 to install these OH groups at several positions, and then you can essentially put all these groups, as protecting groups across to make what you want to make. And the reason nature can make this, because you can imagine this compound has several CH bonds, and it can actually function like specific CH bonds, and they're not very different in terms of their character, and it can functionalize at will, and that makes it get this amazing structure. Now we have been essentially one of the focus in the labs has been to develop methodologies or techniques in which we can convert a CH in a hydrocarbon chain, like maybe something like this, into COH or CX functionalization. As you can understand that putting this OH or X group can significantly alter the property of this compound, and that can have several applications. Now, I want to also talk about the fact that typical chemistry, with all the advances we have had in organic chemistry, with this tremendous power we have in making complex molecules, organic chemistry is not very efficient. The way we make compounds is not very efficient. People who look at things like E factors and all in industry are very high. So, for example, in the pharmaceutical industry, for every gram of compound you make 25 to 100 grams of waste product. In addition, but in contrast, we see nature. Nature does things in a very linear fashion. It is extremely atomic, economical. It doesn't waste anything. It's the most ideal optimized machine you can imagine. So this, in the last, I think, 2-3 decades, chemists realized that we need to change the way we do chemistry. And here is one quotation from Barry Trost, who says that we need to discover new reactions which are very atom economical, so they don't waste anything. it has minimal side products, that it uses, it is inherently safe, risk is very low. And that's one big idea. And the other big idea is that in most chemical reactions, we always do in organic solvents, right? And that's probably the most you use in organic reactions. So could we use more greener solvents like water, or can we do it even without the solvents, right? So these have been some of the areas which chemists have been trying to work on. So how do we find such reactions? So the best way to many of us, the best way to sort of do this reaction is to first understand how nature functions, and then learning some of the principles from nature, can we design some molecular catalyst which does the same function as some of the enzymes they show. And that brings me to this slide. We are talking about, say, functionalization reaction, we're talking about, say, oxidation reaction. And there are this plethora of enzymes, and a lot of them are iron-containing enzymes, which does this reaction in such beautiful manner. They are very specific, very efficient, they works in water. And so the idea is that for decades has been for inorganic bioinorganic chemists has been that could we learn from the way this enzyme function, could we learn these principles, and then could we mimic them in with small molecules. So one of the enzymes which has been really, really, really studied quite a bit, because there are this class and family of enzymes, and they do wonderful chemistry, right? From epoxidation to hydroxylation to desaturation. You name any type of reaction which goes with a redox change in carbon atom, and they do it. It's a very famous class of reaction. It's called cytochrome P450. And if you look at cytochrome P450, what they do is, and as I show you here, in cytochrome P450, you can essentially see that it takes oxygen, two protons and two electrons, and you can see here it has this very hydrophobic molecule, several CH bonds, and it specifically installs the OH group at one position, right? And that's how beautiful or elegant it functions. You can use even not oxygen 2 electron 2 proton, but you can use a reduced form of oxygen hydrogen peroxide. And there is also this class of enzymes called peroxygenases, which are very similar, very similar in sort of the family of cytochrome P450. It also does this amazing. So you can imagine that if you could mimic this with small molecule, and because the enzymes contain iron, it can have a small catalyst, iron compound quantity catalyst, which is earth abundant. We can do selective oxidation of CH bonds. We can activate hydrogen peroxide or dioxygen. Hydrogen peroxide is great because the byproduct is water. Oxygen is also great because, again, the byproduct is either water, or you insert both the oxygen. Or if you can do this reaction in water, right? That would be really amazing in terms of advancing green chemistry into installing specific OH groups in synthetic organic compounds. So for decades, these enzymes have been extremely well studied by both biochemists, bioinorganic chemists, spectroscopists, and we know a lot to know about why these reactions are so selective. As I said, right, there are multiple of this CH bonds, and in cases you get very selective oxidation reaction. And the selectivity comes because, as you can see in all these examples, the starting iron compound has been converted into some sort of high valent iron oxide. Okay, and so here I've shown that you have iron 2 or 3, and you have an oxygen, and you sort of form this iron oxygen bonds. And these iron oxide bonds are extremely specific, including certain CH bonds, and their selectivity can selectively cleave CH bonds depending on their bond strength, and then insert this oxygen between the C and the H, and you get a hydroxide compound. Right? And so that's a chemistry which has been widely studied both in UV complexes, both in enzymes, and we know quite a bit of these things. So how about then, mimicking nature, finding out, we can see a lot of amino acids, we can see cofactors like this. Can we build ligands, and do the chemistry without this big proof? And that's sort of the challenge. Okay? Now, as you can imagine, since P450 and this heme class of enzymes are so popular, and also these non-hemes with tri and tetradentate ligands. So there were decades in which people were trying to use simply the heme, or a very nice mimic of these neutral end donors and iron complexes to try, if you can, essentially do convert a CH to a COH bond, okay, in a selective, okay, manner which is scalable. So that means that, I do in a way in which organic chemistry functions, right? So can I take 1 gram of stage, a compound called stage one, and can I convert that to a hydroxide in a small scale? So the early phase, where in the 80s, in the 90s, in the early 2000s, there was this wonderful chemistry being developed by a lot of great people around the world, but they were really not scalable. They were like, we were looking at substoichiometric reactions. We're looking at understanding. We're doing state hydroxylation very nicely, but they were not in a manner which was predictive, scalable, and all those aspects, which is the hallmark of an enzyme, was not present. I think the field got a huge sort of a step ahead by this 2007 paper by Christina White, in which they reported this complex. And then in 2009, there was Miguel Costas, who came with a very similar format. And then subsequently, we have come up with a few different complexes in which they have shown that, truly, you could design complexes, and you could use these complexes to hydroxylate state bonds. I told in this case, this is one drug, called artemisinin, and you hydroxylate at a position which are not, functional. This is not so easy in this case. And so you could do this in a predictive, selective manner, and they have done. And there's a huge body of work which has come from all these groups in the last one. Okay. Um, a few things which still, sort of was not sort of answered when we started going into the field in the 2010s, 2010, 11, was that they were using stoichiometric acid. So they were, you needed this for the making of the O bond. You were still in acetonitrile, so this is not enzyme limiting because you're not working in water, so you have to use solvents. These were very reactive, so aromatic groups were not really tolerated, but now I think they have new versions which does it a little bit better. But there were several issues which were not still solved, but clearly they were not a functional limit of cytochrome P450. They were not working in water at neutral pH using hydrogen peroxide. So we focused on this series of complexes called iron camel complexes. So these are tetraamido macrocyclic ligands, and I'll give you a little bit of the history of this. They have 4N minus donors, okay, and these are called tetraamido macrocyclic ligands and the iron complex. So these were developed by Terry Collins at Carnegie Mellon, um, in a large program in which they were first interested in sort of saying that, look, we can't blindly follow biology, so we have to make a complex which sort of stabilizes the high valent states, because the high valent iron states are what are the active species. So they started developing polyamido chelating ligands called PAC, polyanionic chelating ligands, sorry, ligands. And then over the years, they found out, so they were trying to learn that what is the ligand design I can do in which these high valence states can be stabilized and the ligand doesn't decompose. Remember, in the protein structure which protects everything, but when you're in a bare solvent with the protein structure, your ligand framework has to be extremely stable. So this was a large 25-year program which came up with this camel ligand, and this is one of the best camel complexes which was developed, very very popular, and these are incredibly good for oxidation. Okay, so they activate hydrogen peroxide at sub-micromolar concentration, and they have been widely used and body of work in environmental remediation, especially in wastewater treatment, microplastics, endocrine disrupting chemicals. There's a startup called Sudoku which is taking this forward in wastewater treatment, and this is absolutely an outstanding peroxidase. Okay, so the point is, it was a great peroxidase mimic, but it did not show a monooxidase activity like cytochrome P450 water in a manner which I was saying. It could not really scale up. The peroxidase activity could be scaled up in large volume, but the monooxidase activity was really not there. So what do you do in the monooxidase activity? So if I take this complex, I add, suppose this hydrocarbon called adenine, and I add any of this oxidant. Can I do I hydroxylate as I would do with cytochrome P450? And there's absolutely no problem. Okay. So this framework was an extremely good peroxidase mimic, very robust, works with water, activates a lot of good things. But this was not a monox. So my student Tagadola Panda, who was the first student to get into this, so he rationalized that so if we sort of change a little bit and synthesize this complex in which this framework, and one of the reasons we figured that this was not very working because probably this was degrading. So we thought that if you could tie this back down by changing from an amide to a biurate moiety, so it would be more planar. And this still would have a lone pair, which would relocalize and stabilize my high valence iron. And so if I have this, maybe I have a system which is more stable and the reaction with the CH bond probably faster than its own degradation. And so that was the idea. And that, essentially led us to making this, this biodate modified iron chemical process. And we made a few varieties of this. And then, Munmun, who was looking at to look at if you could get this reactions going, sort of, showed that if you could take these complexes, we could use acetonitrile in a little bit of water, a little bit of base, and you could use either sodium hypochlorite or MCPDA, not too much, And if you add now to adamantane, you could get very nice hydroxylation of adamantane. So I want to point out here that adamantane has tertiary CH bonds. There are 4 of these. I put a green dot onto them. And there are other secondary CH bonds where my cursor is right now. And the bond energy differences are not too. And what you would find out is that it would very selectively hydroxylate the tertiary CH bond. And it was 100 folds more than the hydroxylation of the secondary. So that was really amazing that, by changing the ligand framework, we could actually get an oxygenate sort of activity, and you had such wonderful selection. And then she went ahead and then tried a bunch of substrate scope in which she also tried to oxidize a few complexes, which a few of the natural products and with moderate to good ease, and she could obtain this. Now, once we were looking into this, of course, all the idea is that you need to understand the mechanism of the reaction a little bit better so that you can develop new and new generation catalyst. So the reaction mechanism was probed in quite a bit of details. The first endeavor was to sort of understand, what was the reacting intermediate. And this was a very unusual iron 5 oxo reactant. The second one, which was in the literature, the first one I've given the reference to you. And this was sort of unusual because it was very stable. The stability at half at room temperature of 4 years, very unusually stable. Unusually stable, okay? But sometimes stability means that if it's very stable, then it's not reactive, right? It was stable in acetonitrine, and we could, take the help of a lot of people as journalism for the characterization using Raman and Mosbar and all of those. But what was amazing was that, it could still, not only if you could add a substrate to it, organic substrate, CH bond, and I've shown three compounds here. And this would hydroxylate very, very nicely. You could see here that what I've shown here is that this would hydroxylate activate the CH bonds even in blue than the ones in purple, right? And so it had very nice selectivity. It was stable, yet reactive. Okay? And so that was very unusual. We have seen this that it does oxidize, and this reactive intermediate was really amazing. Now, since we had an access to such kind of a very stable oxo iron 5, and that time Bashov Dhar was a CSR sort of a postdoc pool officer fellow who joined our lab, and he had a lot of experience in mechanistic studies. So he and my other graduate students looked at the how would this iron 5 oxo react at room temperature, because it was sort of a great way of understanding room temperature reactivity, because it was stable at room temperature. So you could actually form this at room temperature and follow the kinetics and do all the other associated studies to understand how this would react. So we looked at how the mechanism of the CH bond happened, and this is more of the classical rebound mechanism. We looked at the alcohol oxidation and find out that because the camels have this CO carbonyl amide bonds, the alcohol would first come and sort of form an associated pair with iron oxide, then it would react. There was a saturation triangle to discover. So interesting things coming up. We looked at the oxidation reaction. And then Bashov and my other student Shantanu, they together looked at the oxidation of OH bond. So we could show water oxidation using these iron complexes, both in photochemical and electrochemical means. Now, so when this 5-oxo was done, the other congener, which is also very popular in this area and biologically very relevant, is a one-step lower oxidation state, which is the oxo iron 4. And so my graduate student Shantanu, he could make oxo iron 4, which was also easy, and it was reported earlier that in camels you could make this. It's very stable in water. He could make it in water. very stable also in acetonitrile. And then this allowed him to compare these two species very carefully, right? What is the difference between these two? And one of the highlights we found out was that once you went from 5 to 4, the redox potential changed significantly. There was quite a bit of drop in the redox potential. And what changed was the BD iron OH band. So this is a measure of how strong CH bond it can break. And 99 means that it can break CH bonds nearly up to 99 kilocalorie per mole at room temperature. It's an exothermic reaction. You can see that the iron 5 oxo can break strong CH bonds, but the iron 4 oxo can only break weak CH bonds because the BDOH value was 8. Okay. And also if you look at the rates for the same substrate, and this was much faster. It was probably driven very much by the high redox potential of the iron. So this was kind of fun. Right. So next, when we were right here, and the thing right now was that we were having this complex, we were forming this nice intermediate. We could use sodium hypochlorite MCPP, not too nice oxidant. The MCPP is terrible, and sodium hypochlorite also gives you a lot of sodium chloride, and it's very basic, and it's not a very nice. So we were trying to think how to make this more green. So one idea was, okay, till now we had an iron free. We were putting an O atom transfer oxidant like NaOCl or MCPA, and we were transferring the oxygen, and then that was doing the reaction. How about we sort of simply do 2 proton 2 electron oxidation? We have seen in cyclophotometry we can do this, and then we access this. And if we access this, then we can do it without, using something like as nasty as MCPA. So my guided student Big 2, he took up this idea, and what he did was that to use a chemical oxidant would be the potentials of 1.1, so you need a very strong chemical oxidant. So he got away with a mild chemical oxidant like a cobalt 3 pentachloro pentamidinofluoro. But then he took the help of a ruthenium Swiss BP, which was a photosensorizer, which would sort of harvest the energy, and then and the cobalt now could oxidize it to the ruthenium 3, and then at a milder oxidation potential you could do this. And then this was extended to the electrochemical, in which you don't need any of this. And you put it in a simple electron, when you do the 2 electron oxidation, you end up with this, and then you can do very nice oxidation there. Okay. So this is all. So I talked about NCPB, hypochlorite. We talked about electrochemical, photochemical idea. What about dioxygen? And we'll come to H2O2 at the end. What about dioxygen? So the dioxygen reaction of these channels, okay, are also fairly well known, fairly well studied, known earlier also. So if you add, if you take this weak water aqua complexes, if you put in a solvent like dichloromethane, which is hydrophobic, oxygen is known. You see that the color from yellow, which is this red, completely becomes black. But what is interesting for us is that in this black complex, which we characterize as the iron 4 dimer, which was also characterized earlier, if you add the cyclooctene, the spectra immediately goes down, and you get very clean, okay, epoxidation reaction. Okay. And that allowed us to look into the kinetics a little bit carefully. And what we figured out is that this species is mu of the dimer is in the equilibrium with the iron 5 and the iron 3. And addition of the substrate sort of, and the iron 5 reacts, and that drags the equilibrium, and that's how the reaction goes. We could find the rate law, we could find the kinetics, and the rate law really, fit in very nicely. Now, then we could simply take, this complex, water complex in dichloromethane, you a little bit of heat, 50 degrees maybe, and you could get a few oxidation reactions going as a proof of concept that you could use completely oxygen and there's no oxidant, right? And you could clean. Okay. So again, I'll quickly talk about the mechanism. So you have the iron 3 oxygen bound. This from the mu oxo. This is in equilibrium between the 5 and the 3. And the 5 reacts, and the more the 5 reacts, this breaks down, and then it forms the 3. The 3 binds to oxygen, and this reaction keeps on going. Now, if this is true, oxygen binding to the iron 3, that's something which we are very interesting, because everybody has heard about hemoglobin, and excited that an oxygen bound iron species. But we were never able to isolate the one which I put in, because it was, bubbling oxygen, it goes all the way to the iron 4 deoxo. Because we believe the moment this forms, it sort of comes in, it forms a pi box very quickly and it dimerizes, and there was no way we could track it. But very recently, my colleague Jyotisman Dasgupta in PIFR, he was, this is a few years back, and he works with this Puditas palladium, tetrapalladium cages. So these are water soluble cages, which are very hydrophobic inside. So imagine it's like method inside, but outside is all water. So in this case, what he observed was that when you put this, you add this complex and this cage, the cage goes inside the complex, binds to oxygen, and gets locked inside them. Unusual, very, very unusual observation, and over the time we have figured out, from the Mosbart data, from the EPR, and from Raman studies, that this is essentially the iron 4 superoxide. Okay, so the iron 3 binds to oxygen, an electron is transferred, not like hemoglobin, but one electron higher. And so you have S equals to 1 for iron 4 and a half, so you have a 3.5 species, which is are active. The Mosbart is very characteristic. You see the superoxide O's. Okay, and so we could not characterize it in solution get the iron oxygen bound species, but in a different way we could figure this out what this looks like. Okay. So till now I have talked about that we have now been able to convert get do synthesize a complex which is a slight modification of the prototype iron panel which I talked about, and then you could use it in organic solvent to show oxidase reaction with hypochlorite or anything. Okay. Now, but we are always a little worried because it was not really green in that sense, because we're still using organic solvents, it was still hypochlorite, MCPVA. When you use dioxygen, you don't get hydroxylation reaction, and when you use vinil peroxide, it does not. The reaction doesn't work. Okay, with this compound. Okay, so this is good, but this was not a functional mimic, and this is not really great because similar chemistry has already been reported, as I showed in my earlier. So we really wanted to get this chemistry in water using. Now there are several challenges. One challenge is the hydrolytic stability, which the camel, has been designed to sort of overcome hydrolytic instantly. The second major issue, which comes up is when with hydrogen peroxide. So when the hydrogen peroxide binds, you could give rise to both, a heterolytic cleavage or a homolytic cleavage. The heterolytic cleavage would give rise to oxide, and that's what you want. That could give a very specific reaction. But if it somehow cleaves homolytically, and then you get an iron 4 oxo and then OH radical, then the reaction will have no specificity because the OH radical will dominate the reaction. Okay? So you have to control the heterolytic versus homolytic. Okay, and also if you still generate the oxygen 5, it also always remember that water is present. Water can attack the oxygen 5, and that water oxidation could be a complicated side effect. So this is a challenging reaction to do. Now, my colleague Rahul Banerjee, who works with TOF materials, what he did was he took our complex and put it into a cup. I talked about this palladium complex, so the cup is very hydrophobic inside. And now he could do this whole reaction in water. So he could solve the problem of doing it in water, but putting in a cup. Okay, but he was still using hypochlorite and oxygen. Here is another example, not from us, but from Ward's group, in which they put this into a biotin in a protein environment. And so the protein has this hydrophobicity in the cavity, and that was used for oxidation and for kinetic resolution. Okay. So what is the problem? Okay. So as I said, that we were not activating hydrogen peroxide, first of all, and we were not being able to do this in water. So the two things which we figured out is, we know that the camel, there's a lot of literature that camel is extremely good for oxidase, and being used for so many environmental applications. Some of the studies has pointed out that in some likelihood, the active species are either dimeric, iron 4, iron 3, iron 4, iron 4, or some monomeric iron 4 species. So those are essentially, the active species when it works as a peroxidase in 100% water. And so we thought that maybe, the iron 5 oxo in water, which especially with hydrogen peroxide, is not a very good option. It doesn't form in water well. And that is the reason it doesn't show oxygenate activity in water. So one of our hypotheses was that maybe the hydrogen peroxide does from the oxygen 5, but maybe it immediately reacts with the iron 3 and forms, the mu oxo dimer. Now, this peroxidase and these mu oxidimers, the two are wonderful peroxidase, and people who are interested can go and follow out the work on environmental remediation. We have taken a slightly different route. We have used the peroxidase activity. My students, Varmana Malvi and Shukma Kumari, now it's 10 years back, have used this to look at not an environmental remediation, but as a replacement of the enzyme hot release peroxidase in analysis of protein. So, for example, we could, make a complex which would be used as a probe for activity-based protein profiling, and you could actually run this in gel and do a ABPP onto gel. So this was a new sort of application for these sort of complexes. And then we would take this mesoporous, silicon nanoparticles and put this catalyst inside them and decorate with antibodies, and then we could show that we could sort of detect femtomolar protein. So peroxidase is what these are very good at, and maybe there's a good chance that they form either some of these monomeric iron 4 or these mixed dimers, which sort of go through this way. Now I come back to the dimer because that's very important for the last part of my talk. So when you take this iron 3 complex and you add, we've seen this dimer also not only in water, but also we see this in organic solvent. How? When you take this complex and you add half a equivalent of MCPDA, you saw this wonderful dimer forming, and I've shown you this spectred ATP, which is very characteristic of the dimer. Okay. Now, what we typically do is that, so the reason we see this happens is, so you can form that dimer differently. You can make iron 5 oxo, okay? And if you add iron 3 to iron 5 oxo, it form proportionates it form a dimer, okay? So you can add half equivalent to MCPD, or you can use comproportionation reaction, and you can make this dimer and characterize it. Now, the good thing in acetonitrile using NaOCl or NCPD is that when you add NCPD or NaOCl to this dimer, it cleanly makes your iron 5, and that is your active oxidant for the oxygen reaction. However, to take this and add hydrogen, if you take this dimer and add hydrogen peroxide, it does not convert because probably the NOx iron 5 oxidizes hydrogen peroxide, and you never get it converted. So we hypothesize the problem is that the formation of the dimer is what is inhibiting formation of oxo iron 5 within hydrogen peroxide. Okay. So how do you stop dimerization? So we go back, to old literature. Jim Coleman, taught us that we could make certificate for porphyrins for binding oxygen. We have also seen in work of Christina White that they've used in very nice sterics to sort of control the activity. So my student Shondipan, he came up with this idea and said, look, what we do is that we put a little bit of sterics, and put a little bit so that it does not affect substrate coming in, but is enough to stop dimerization. So he converted, so the prototypical complex, the two dimethyl groups here, so there were two methyls and two methyls here. So he converted this to a phenyl. So we first with the residuc, now we have the enantiomer structure. And you can see here, that this is made in such a way that one methyl is up and one phenyl is up and one phenyl is down. Okay, so one phenyl up probably could stop the dimerization while the other side is empty for the substrate to come in, and so that was what we had sort of. So Shondipan and my graduate student Pooja, then they tried to figure out that if it would form oxo iron 5 in water using NCPD and hydrogen peroxide, and it did form, and we could. It's very reactive. It's not very stable as the in acetonitrile, but we could, trap the oxo iron 5, and we could see a very characteristic ETR half. This 1.75 is very characteristic of iron 5 oxo. We could also get the Moss bar. The Moss bar has a little mixture, and so we could fit it. But the main component was an iron 5, and so that was and so we could essentially make this generate oxo iron 5 in water. So since you could make oxo iron 5 in 100% water, that was a great thing because we could study the reactivity of oxo iron 5 in water, right? And that's, even though there is an oxo iron 5 reported earlier by Colin Street, but doesn't do CH activation in water, 100%. So what we could see is that you could do this reaction, and the reaction kinetics was just the same. The kinetic isotope effect was 10 for cyclohexanol. We had to choose a substrate which was water soluble to ensure that we could do the kinetics and all. And what was really amazing was the reaction rate was 350 times higher than what was in acetate. Okay, and this is something which we are studying, very intensely right now, and we see some amazing hydrogen bonding effects, which we also observe in secondary solvent kinetic isotope effect, and we see in the activation parameters that we have very organized state And water essentially hydrogen bonds to bring down the activation state and make this fast reaction. So water not only is a clean solvent, but also accelerates the reaction. That's very important. And so then, Shandipan and Pooja, what they could do is they could now, because it was working in water, it was working with hydrogen peroxide. So now what you should do in acetonitrile using MCTBA, now you could do the whole thing in water using hydrogen peroxide. And you could see that these are very reasonably nice. What I want to point out to is two substrates. This is trans dimethyl cyclohexanes and trans tetraene, okay? And these are very good substrates because, they are very difficult to oxidize. Because what happens once you do the stage bond extraction, there's a radical form, and it has an incredible propensity to epimerize. If the rebound is not very fast, they epimerize, and you always get a mixture of season. Most complexes, at least I have seen in literature, always gives you a mix of season trans. But in this case, you could get absolutely 100% trans in water. And if you do it in acetyl, I'll show you that you always get a mixture. So here is a comparison of what happens in water versus acetonite, right? And you can see here that for the same complex, red is acetonitrile and black is water. In acetonitrile, the cis trans is 7624. In water is 100% trans. The cis trans is 3862 and it's 100% trans. Okay, so you could see that water, okay, not only it gives you a greener and a cleaner solvent, but it also accelerates the reaction. It accelerates the rebound reaction in all likelihood, and it gives you much more stereospecific selective reaction than it would happen in this. Okay. And of course, they could now do this for other substitutes. Now, once we're done with this, I will now talk about in the last, I think, 35 minutes, or last 5-7 minutes, I was going to talk about two applications which go beyond small molecules. And that will introduce to another class of another advancement which we have done and which we are very happy and which we are very proud to sort of do. The first is, so we all know about the plastic issue, especially in India. So here is the data at the bottom of the slide. So if there are 367 millions of single-use plastics produced, and a lot of significant amount of them is this waste littered around, all over the place. And I've shown you some of the large class of plastic people use. Leave out PET because that's the most recycled plastic. In India, we have nearly 90% recycled PET. But these are the two ones which are the least recycled. LDPE, polystyrene. Polystyrene is nearly non-recyclable. And the interesting part is all of these also have seeds form. And so that makes it interesting substrate simply because if I can now, I can have a hydrophobic long polymer. If I can now functionalize them and put OH into some of the seed forms, then I bring polarity into them, it completely changes the problem. And they can have several applications as adhesives and all, because the part of them is hydrophobic, some of them will be hydrophilic, so they can sort of bond between both the hydrophobic and hydrophilic. So these are applications, and these are synthetically difficult to make. Okay, and so we said that a good application would be to not look at only small molecules, but could be sort of upcycle this, because then if you can install these, the value increases, and this is what is called polymer upcycle. Now, again, this is not new. As you can see here, this is also very dated. There has been a lot of attempts on it, and I'm showing two examples. I think there are more examples in the literature. But one of the, forget about the oxidant that it's MCBD, I'm not going to talk about it, but what I only want to point out is this. These polymers are very insoluble, and most of the cases, if you have to do a homogeneous reaction, what you need to do is that you need to use solvents like dichromethane, dichloroethane, and these are solvents it's not possible to do for any practical application. So how do we do? Okay. So what we thought was that could we use these polymers, and my student Deboshvita and undergraduate Anish, they were working on this. They thought that if you could take these polymers and if you could install the OH groups onto the back, okay. But the problem was that these polymers will not be soluble in either acetonitrile or water, forget about it. These are just not going to be. So what they thought was that could we use solvent-free mechanochemical grinding, or in a ball mill, okay, to see if we could do this hydroxylation there. And we had a very nice choice of an oxidant. The choice of an oxidant was something we use in our washing powder. This is sodium percarbonate. And so what they did was they took some bit of sodium bicarbonate, which is hydrogen peroxide, and there's an A2CO2.1.5 for oxygen bleach, which you use in a laundry detergent. You had this new modified tannin complex, and then you could sort of grind it together and see what happens. And what they found out that with small molecules, okay, within time frames of 45 minutes to hour and a half, you could do extremely good, hydroxylation reaction of small molecules, solvent free, completely solvent free, simply either mechanochemical grinding or in ball milling. And what was again amazing, I sort of was trying to point out that from acetonitrile to water, we made a huge jump in terms of reaction rates and selectivity. And when we went to solvent-free reaction, the selectivity even went much higher. The reactions were much faster, much more, selective, and the enhanced 3 degree to 2 degree selectivity. And this was really, 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 really nice. And then what we could do is we could go ahead and take, this was a model polyolefin, which is poly-1-hexene, which my colleague in chemical laboratory had synthesized for us, Amit. And what we could do is we could take this polymer in a ball mill or in a simply mechanical grinding, and we could actually, for do it for an hour, and then we could find out that we could install a few O-ring screws very, very specifically at the back. And the good part, and we could do the same thing in polystyrene. And what is amazing about polystyrene is that polystyrene CC bonds are very prone to change. For most oxidation we do, the polystyrene CC bonds will change, the change will happen. But here, the GPP was virtually the same. So we were not breaking the polystyrene, but we were installing hydroxide groups, up to 10 mole percent in the diagram. Okay, so proof of concept that you could use it in a solvent free. And this was very nice in the sense that, enzymes do need water and solvent, and you could sort of push this reaction beyond the realm of enzymes to do it in a solventless function. So since CH bonds were very easy, what we could also do was we could also, so before that, let's talk about the mechanism. We looked at the mechanism of the reaction as best as we could do in the solid state. And UV spectroscopy, the EPR, more or less was showing that under those blending conditions, somehow the oxo iron fibers being generated into the active oxygen. Okay, so the mechanism probably did not change too much, although we were not being able to do as many studies as we could do in solution to get the exact specification. Now, since hydroxylation was working very nicely, the other reaction was alcohol oxidation, which we knew would be much faster. So alcohol oxidation was attempted, and this was very, very, very nice. And I'll tell you in a minute that why we went to do something, looks like very mundane alcohol oxidation, because we were interested not in this substrate, but in this substrate called cellulose. Because if you look at cellulose, cellulose is a large carbohydrate polymer and also has a very nice primary alcohol, okay, and also has very nice pH bond. And one of the things with cellulose is very insoluble. We take cellulose, processing of cellulose is a nightmare. So one of the things which is being, widely being done, and there are so many companies, so many people working on it, is to take cellulose from a waste material and then convert it into forms like a nanocellulose, which is more of a rod type, or spherical carboxylated nanocellulose. Okay, and these are something we tried quite a bit. So we figured out that okay, we have this complex. Okay, we know that we could do oxidation of polymers in the solid state. We know that we could do alcohol oxidation very fast. There are CH bonds we could break. If we could break the CH bonds, we could definitely, depolymerize it somewhat. Okay, and then can we make either this fibrils or this carboxylated nanocellulose? Because these have now a lot of different functions. Because you could make a list of things which you can do with them, and they are very popular in that sense. Okay? And so here is the experiment. So we could take cellulose, where we could do mechanical grinding or ball milling, and what we ended up with is very nice spherical particles. Okay, and this is the AFM FEAC, right? And this was not the end of it. Okay? Then we decided, okay, now getting into cellulose is a very environmentally fast process, right? You could take the pulp, take out the lignin. That's a nasty process. Actually, camels have been known to oxidize lignin, for a long time. And in the paper pulp industry, they have some applications because they could oxidize lignin. In this case, what we thought that could be in the solid state, okay, take a lignocellular biomass, okay, and if you take a lignocellular biomass, I could essentially decompose lignin, that is known, that's a peroxidase activity of cannabis, and that is known, and also break down the cellulose. So I can take a lignocellulose mass and in one step make this nanocellulose, okay, and which could be a really a step ahead. Okay, and so here is it. So we took corn cob, okay, which is a waste material, and we took fine softwood, and then we could do mechanical grinding, and in one step we could actually get this carboxylated spherical nanocellulose in one step, and by just washing and okay. I'll show you one application of this material which I really like. I keep on spilling, the Indian curries on my shirt, and it always goes yellow. And so this nanocellulose are hydrophobic inside and are water dispersible. They're hydrophilic outside. And so if you sort of take it and put it on a surface which has a hydrophobic thing, it actually sucks it up, and it's supposed to sort of take the dirt out. And we have shown one application, and this is turmeric, which I was talking about, and if you take turmeric and this is water, if you take turmeric, wash in water, nothing goes in. You can use this detergent, and you can see it goes, and you can use this spherical nanocellulose, you can see it up very nicely. So there is a potential. Okay, so this is my last slide. So we started synthesizing a new version, okay, a version of the classical trimer, which is exceptional for oxidase with hydrogen peroxide and terminal oxidant. We could convert that to an excellent monoxygenate inorganic solvent with NCBD sodium chloride. And then with one more modification, we now can do this reaction in water with hydrogen. So that's the journey we had the last, I think, 2010, last 14 years with this. I think I'll skip this out. We're out of time. I have to acknowledge, these are the my PhDs, postdocs, and PhD students who have worked with me. The names that they are, I've acknowledged them in slides, so I'm not going to talk about them. Lots of master students, I couldn't put all their names, but Kane Helen, who was worked really hard on the electrochemical oxidation reaction. Amrita, who did the work who worked with Devasmita on the polystyrene, polylexine oxidation, and Anish is doing this cellulose work. Let's see, it's particularly mentioned because I've talked about their contribution in this talk. And lots of collaborators, wonderful collaborators, and the funding from GFT and IISER Kolkata. Okay, and that's a picture of the group, and that's a picture. Okay, so thank you very much. I think I am a little more than 45 minutes. Okay, but Neha told me that I could go 5 minutes ahead, more than 40. So it's probably okay. Still have some time.
Thank you so much, Professor Sen Gupta. It was a lovely and a wonderful talk indeed.